So hello everyone, welcome to Cheenta. So as you know, or probably you do not know, I'm the first one to tell you um, the mathematical statistics syllabus of IIT JAM for 2026 has changed. So I will help you understand two things. You will get to know two things at the end of the video. Number one is what is the change in the syllabus, and number two is where to read, where to start reading it from. Okay, how to enhance your knowledge. So let's first go into the syllabus. So this is the official website of JAM 2026. It's being organized by IIT Bombay. So now let's understand a few more things, like mostly what is being added. One topic that was not mentioned in the 2025 JAM, but it's already usually taught, is the lim sup and lim inf of sequences. It's already in Cheenta's syllabus of real analysis, sequence and series limit 1 and 2 and 3. In matrices and determinants, or rather linear algebra, one extra thing that is added is quadratic forms and its properties. We've also taught that before in Cheenta under linear algebra, uh, lesson 13, quadratic forms. In statistics, there are three whole new sections. There's descriptive statistics. So descriptive statistics, as you know, it tells you about, gives you a description of the data. Okay, one-dimensional, mean, variance, measures of central tendency, dispersion, moments, central moments, bivariate data scatter plot, and correlations, and all these things. So this is usually very core to any statistics curriculum. Um, I would suggest the following resource. This is a notes by Professor Tanujit Chakraborty. He has a descriptive statistics notes on his website, and you can read this and you will understand the fundamentals of descriptive statistics. You please also feel free to use the book that is suggested in your university at your university or college. Okay, the next simple addition is in limit theorems, where they are teaching convergence in mean square almost sure convergence, and added strong law of large numbers. This is also something uh, we have taught in Cheenta in our course in limit theorems, and it will be available in any probability book. There's another interesting addition in probability theory, that is stochastic processes, the section 12. I am always a big fan of this probability book, and I suggest this to all the students. Okay, so Introduction to Probability by Joseph K. Blitzstein and Jessica Hwang, and the stochastic process is already like it contains two aspects. One is Markov chain and one is Poisson process. So as you can see, it is nothing but the 11th chapter and 13th chapter of this book. So this is what you just need to do, and if you are following this book, this is not hard. Okay, Markov chain. So the basic idea of Markov chain is nothing but, usually in data in x1, x2, xn, we assume that x1, x2s are IIDs, right? But let's take a time series data. But x1, x2 has a natural dependent, like the stock market price tomorrow has a natural dependence on the stock market price today, and there's the xi's are not uh, independent. Okay, so in this case, uh, if there's such a sequence, then where will the limit go? What is the behavior of the sequence of such random variables where there is an interrelationship? So Markov chain is based on something called Markov property, where we say that the dependence, or like xn, the dependence of xn is, of course, xn is dependent on past data, but it just depends on the immediate past, like xn minus 1. So if you see the syllabus, they have discrete Markov chain. Okay, discrete time Markov chain. So that is helpful for you. Um, okay, so Also, there is Poinsot process. So Poinsot process is another interesting idea, and I believe it's a really good generalization of Bernoulli process. So all the discrete distributions you get, geometric distribution and binomial distribution, all these things are output of uh, Bernoulli process, where Xi's are Bernoulli trials. So it's a process is nothing but just like, okay, so Markov chain is a process, stochastic process, right? So similarly, there is a Bernoulli process, X1, all are IIDs, independence bound, IID Bernoulli random variables. And if you calculate the interarrival time, that's where the geometric distribution come in discrete format. Now, if you want to, for example, geometric distributions continuous I would say generalization to continuous time is exponential distribution, and hence Poinsot process is nothing but a generalization in continuous time for Bernoulli process. The generalization of that is Poinsot process, and the interval time there in Poinsot process is exponential distribution. This is beautiful, actually. I have mentioned this in one of the videos on the channel, so please do check it out. So Poinsot processes therefore helps you understand it's a continuous time distribution, and it's actually really beautiful. So the good continuous distributions naturally come out of this um, Poinsot process. Interestingly, it's actually really beautiful. So this is what is there in probability theory, and that is added the stochastic processes. So then the section 11 that is added in statistics is non-parametric methods. So for non-parametric methods, I will suggest you two books. First, I will suggest you to start with Mathematical Statistics and Analysis by John A. Rice, because I already suggested this to students who are introducing themselves to statistics, because it's more easy to understand. So before we go ahead to explore the books of non-parametric statistics, we should understand that what is non-parametric statistics doing, how it is different from parametric statistics. So usually non-parametric statistics is about, let's say, if I ask you the question that I give you two data points, two samples, okay? I collect samples from a distribution. I do not know the distribution. I collect samples from another distribution. I do not know the distribution. Since parametric statistics and statistical inference, we assume when we take sample from the data from the population, we assume that the population is following some probability distributions, right? Let's say normal distribution, or let's say, yeah, basic thing is that I have two normal distributions. I select sample from them, and I want to test whether their mean is different or not, right? This is a basic parametric statistical inference. So the population is parameterized by a normal distribution, which is again parameterized by its means. But in non-parametric statistics, we usually do not assume such parameterized statistical distributions. So we will ask this question that, are these two distributions same? Like, I do not know the underlying distribution, the probability distribution of two population, but I know that there are two different population, and they can be their population can be, the distribution of the population can be same. So how can I use this sample, let's say x1, x2, or xn, and y1, y2, or ym, these two samples, and understand whether their distribution is same? So non-parametric statistics actually uses this kind of attacks this question and solves this question without distributional assumption, and it's beautiful how they do it. So they use, instead of, so what do we do in parametric statistics? So we take x bar and we take the y bar, we take their difference and normalize with some standard deviation, and then this quantity, this statistic, it turns out to have a distribution, okay? And then once we know the distribution is easy, the process is same. But in non-parametric, this is what happens. This whole process happens in parametric statistics. But in non-parametric statistics, we usually, since we do not know the underlying distributions, we usually have no information. So what we do is, interestingly, we do something like using ranks or interpair distances. Okay, we use ranks and interpair distances to understand that, are these two functions different? For example, in this man for example, in this Man Whitney test or U test, um, if there's x1, x2, xn, and y1, y2, ym, and you want to test whether their distribution is different or not, right? So what you do is very simple. You combine all the samples, let's say m plus n samples. Let's say x has 10 samples, y has 20 samples, sample size, and you add, like, you combine them together as if you don't know from where it came. So, and then you have 30 sample now. Now you rank them in increasing order. Okay. Now understand, if you rank them, if two distributions are same, their average rank will be same, right? But if two distributions are different, okay, then what will happen is that um, one's kind of mean or set of points will be skewed to one side, and another distributions mean like set of points will be skewed to another point. So their difference of individual rank. So now once we have this 30 points rank, we now pick up the x group ranks and the y group ranks, and then we average their ranks and see, or add their ranks and see that what is the difference. If the difference is high, that means their distribution is different. If the difference is low, we do not have enough reason, enough data points to reject that their distribution is different, right? uh, Reject the distribution is same. So yeah, so this is how they think. And this statistic that we have computed in terms of rank turns out to have a distribution called U distribution, sorry. And sometimes we also approximate this using normal distributions for large sample. So this is the beauty of non-parametric statistics, where, and you will see while you do this, a lot of probability and combinatorial arguments come up beautifully. And this is beautiful. I love non-parametric statistics. It's really beautiful. So yeah, similar ideas are there in non-parametric statistics. And I think the basics to excel in non-parametric statistics is to actually excel, actually understand parametric statistical inference really well, and also combinatorics really well, and probability and classical probability really well, so that you can compute, because its ranks and everything are classical probability. Each sample has same weight, right? So okay, so yeah, I was excited because non-parametric statistics is beautiful. So now this book doesn't contain all the syllabus, but this is a good introductory book. It helps you tune your mind with these new ideas that I have shared. But a book which contains all of them is this step-by-step approach to non-parametric statistics by Corder and Foreman. These books will actually give you the entire syllabus. So go ahead and search them in the book and read those specific ideas, make your own notes, and start learning. So to revise, Descriptive Statistics notes by Tanujit Professor Tanujit Chakraborty. For probability, for Markov chain, use Introduction to Probability by Blitzstein and Jessica Hwang, Joseph Blitzstein and Jessica Hwang. The 11th chapter and 13th chapter. For non-parametric statistics, first use Mathematical Statistics and Data Analysis by John A. Rice, and non-parametric statistics, a step-by-step approach by Corder and Foreman. And this will actually help you cover everything you need, and enjoy learning statistics, enjoy learning these beautiful ideas, and fall in love with statistics and data science, and build your passion for it. So all the best, and hope to see you in Cheenta classes soon. Bye-bye. Yeah, let me stop sharing